And the other is a cosine squared, cosine of doubling, which is cosine squared minus sine squared. And there are few modifications of this formula that could be done depending on the exercise, and this is pair of these other two identities that can always try to utilize if we want to. They come out right from that sine squared plus cosine squared is equal to 1 formula. So that's the one that we have. So anyways, we're gonna use this for solving some exercises. And if you aware of these identities, of these formulas, then you can definitely right away get the exercise solved, just plug numbers in. And the only thing you need to watch out a little bit, if that's a positive or a negative. Those are the only two things that we need to be careful with. So I'm gonna try to solve some, I think I saw nice equations that utilize these formulas. They were, I think, somewhere at the end. We haven't seen trig equations for a while. So let me do, let's say, problem number exercise 69 recommended in this section that wants us to solve equation that says cosine of double angle and also 6 sine squared, and this is equal to 4. So we can utilize the formula for cosine of double angle to bring it down to the single angle, because we need to have always the same angles when we solve equation. And since we're dealing with a sine, then instead of using that favorite fact that sine squared plus cosine squared was equal to 1, so I could replace here my sine squared with 1 minus cosine. See, I never memorized those formulas. I think instead of having a hard time memorizing, you can always derive those. So, oh, sorry, I wanna, oh yeah, that's what I'm doing. So I lost track a little bit. So we got a now cosine squared of theta, and then we subtract, so we change both signs. So it'll be minus 1 and plus another cosine squared of theta. In other words, we have, instead of a double angle cosine formula, it'd be 2 cosine squared subtract 1. So we go into, I think I wasn't careful, I need a sign actually, right? But anyways, it's good that I made this mistake because I shown you one of these formulas, and now I need to show you the other. That is how it comes out, and it'd be coming out exact same way, right? But now I replace my cosine with 1 minus sine squared, right? Because, say, I wasn't careful. I need sine. I need to write it all in terms of sines. I don't want to get even sine and cosine in my equation, because that way I will have to, well, actually utilize the same process again. So why don't I utilize it here once? So looks like 1 minus sine squared, and there is another minus sine squared. Maybe I'll underline this with green, so it'd be a little less, a little bit more straightforward. So this green stuff is what I care about. So it'd be 1, subtract 1 sine squared, and then subtract another sine squared. So that'd be subtracting 2 of those sine squared. So anyways, these two formulas replace my cosine of 2 theta depending on the exercise. And that's actually why I wanted to do this problem, to show you that you can always manipulate with this. So now I go with the replacers. So cosine of 2 theta, I put this 1 minus sine squared, right, of single angle theta. So we've got same angle, and that's what counts. And we also can put these sines together, so I can put them together and get 7 times, actually 6 minus 1 is 5. You need to be careful with arithmetic. Sine squared, right? And also I can bring the number 1 over, just minus 1 on both sides, and get that it's equal to 3. Okay, whatever it is, it's fine with us. So we can actually start the process. I just think I wasn't careful because this is 2. See, I need something's wrong with me today. So 1 minus 2 is going to be, actually 6 minus 2 will be 4. 4, right? That's what I should be watching out for. So maybe I can just carefully erase this. So 1 minus 2, and then 6 and 2, when I subtract, I get 4. I don't get 5, it's 4. Okay, whatever it is, I need to get my sine pulled out, and I see that sine squared of theta is 3/4. And now I'm going to do the square root on both sides, right, to get sine itself. Now, when I do the square root, always plus minus appears. So when I extract the square root, and here and there, we get a square root 3/2, but and positive and negative squared gives me 3/4. So we have to consider all of those. So how do I solve this equation? Remember, make a picture of circle, right? Square root 3/2 for the sine is one of the very popular angles. Deals with either 30 or 60 degrees. And if that's a function sine, then we get y coordinate of the point on the circle here. It looks like this point corresponds to the big angle, right? Which is, so this coordinate will be a half, and that will be radical 3/2. So the angle I'm working with is like 60 degrees, or people call it as pi/3. And there'll be another point here that has exact same y coordinate, and the same with the lower one. So the idea is that I have 4 symmetric pieces on my circle, so it's pi/3. Then that be 2 of these pi/3, 3, 4 pi/3, and then 5 pi/3. You see all of these pi/3s here. So I cannot take period of pi/3 for my solutions, because these 2 points will be included if I just go by pi/3 all the time. So what I do is I describe those 2 points with period pi. So I can say theta is pi/3 plus, instead of 2 pi n, I can say pi times n. So I describe those 2 that I put with crosses. And then the remaining 2 will deal with just pi/3, or 2 pi/3. And also period is pi, half rotation plus pi n. So this is my general solution. And if they want in the interval 0 to 2 pi, well, we have those 4 points pictured on this unit circle. That's why I think the best way is to always make a picture, because otherwise, if you just utilize these formulas, you might get mixed up with arithmetic, with this pi/3, all this. But on the picture, it's always nice and symmetric. So the idea is that we were using these double angle formulas, and that's, I guess, the point of this section. Now there were also half angle identities, right, that we derived. And I think it's very good that I actually posted both of these, because from them I can pull out half angle identities right away without even looking for the formula sheet in the beginning of the book or at the end, because the idea is you can always derive them. So I want to pull out this guy, cosine. And to pull it out, first of all, I bring one to the other side. So I get a cosine 2 theta minus 1. Divided by 2. And since I want to get half angle, then I'll put half angle here and then whole angle there, and it'd be a square root. And analogous from the second one, I can pull out sine squared and extract the square root, so it'll be just a sine of half angle. And when I pull this out, it'll be now sine goes to the left, so cosine is subtracted. So it's actually, let me see, I should be careful. So here is plus, right? Because it was minus 1. So I bring that thing to the other side as a plus 1 to isolate cosine. And here will be then minus, so it'll be actually sine, and that's 1 minus cosine of this divided by 2. So you could always double check these identities because you don't have to memorize, but you should be able to find them. So let me get an exercise here and do number 76. I think that's an awesome choice. So let us try 76. That says cosine of 2 theta plus 5 cosine of theta. So it looks like this will be similar to the problem I just did, problem 79. So it's not with half angles, but let's do it and then we can take a look at something with this half angles. Good idea. So I'm glad that you get interested in this. So I'm gonna get a little room and let's see another equation. So in 76, I have cosine of 2 theta to replace, and now we need the cosine of theta. So now I need to use the formula with a cosine of theta. So instead of cosine of 2 thetas, I should write it as a pulling the cosine out. So how can I pull this out? It'll be a cosine minus 1, and this is, oh, I was erasing as part of this got erased. Very nice. I was erasing on the left, part of it got erased on the other side. So anyways, so if I square both sides, I have cosine squared, then I multiply it by 2, I get 2 cosine squared, and then minus 1. So it'll be 2 cosine squared theta minus 1. So this is what I'm going to utilize for working out with this problem. So let me write it down. It's a cosine of 2 thetas, and we add it with 5 of these cosines theta plus 3 is equal to 0. Okay, so number 76, right? That's what you were asking me to do, and let us enjoy it. And first of all, of course, it's always a good idea to double check your identity, and the way to double check, so page 525, so I can show you where they all are, and then return back to page 525. So my formulas, because if you use the wrong formula, then definitely you're never going to get correct answer, right? Waiting for it to open for me. Okay, so I need to see cosine of double angle, and it's way on the right. It looks like the one that I have here for you was 2 cosine squared minus 1 is exactly the one that I'm using. Now that's a good start, because if you start using the wrong formula, then it's a bad start. By the way, you can right away double check the sine of theta over 2, which is here, 1 minus cosine, and the cosine of theta over 2, which is there, which is 1 plus cosine. So looks like it's fine. I put cosine plus 1, but it doesn't matter, they commute. Now here is positive or negative, and I deliberately don't write this because it's either positive or negative. So we're gonna check this out. Okay, so let's work this problem now. So I replace with my cosine double angle this 2 cosine squared and also minus 1. And then copy the rest. So it's 5 cosines. And then also plus 3 is equal to 0. So it looks like I'm getting here analog of a quadratic equation. So that's cosine squared plus 5 of just cosines. And then 3 minus 1 is 2. And I need to factor this, and it factors similarly to, let's say, 2x squared plus 5x and plus 2, which pretty much factors uniquely when you try to solve this. You factor first term and the last term. First term is 2x times x. That's the only way to factor it. And the last term will factor 1 times 2, because this way I'm going to get exactly 5 in the middle. So this is 4x, and this is x, so you get sum of 5x. So analogously, I'm going to factor my equation with cosine. So just instead of x, I'll put cosine. So it'll be 2 cosine theta plus 1. So you just look at this parentheses, and instead of x, you put cosine. And instead of x in the second parentheses, you also have cosine of theta plus 2. Just like that, is equal to 0. And this is great start, because now I'm going to have to set each of those equal to 0. So either first or the second. And then, well, see if I can solve these if they have solutions. So cosine theta is negative 1/2. I bring 1 over and then you divide. Or the other equation that makes no sense, because cosine theta is never equal to negative 2, right? Because cosine is in between 0 and 1, so negative 2 is not permitted. Negative 2 is here, so there's no answer, and that makes life easier. But for negative 1/2, we do have a couple of results. So there will be points up here and down there, right? And we just had seen them in the previous exercise. They're pretty popular. Looks like pi over 3 twice, because that's 1 pi over 3. And then 4 pi's over 3, which is here. And that's our pair of answers. So we have the answers on the interval from 0 to 2 pi. So we're done with the exercise. But I like to write them with the general solution. So how to put it down? Well, I like to put them down as 1, so I can do the following way. I can say plus minus, because one could be plus 2 pi over 3, and the other could be minus 2 pi over 3. And a period for the function 2 pi k or 2 pi n, as long as this is integer, it works. So another nice little exercise. Please notice, you know how to solve quadratic equation or factor in general, and then each factor is equal to 0, and then you have 2 little equations for yourself to enjoy. Now, do I remember the page? Was it 525 or something? Let's see. 525. Because I wanted to also do a problem with that half angle. Say, oh, 492. I think that's a real page 492, but on this, let's see which section we're coming to. Yes, on this actual book, this was, see, I use that 5 something because this way I can get to it faster. But indeed, 492 is in reality, right? This is the one up in the upper left corner. So I wanted to take a look at the half angle identities, the ones on the upper right corner, just to maybe do a problem to make sure that we start to feel better about them. And let's try something like problem part C here for exercise number, let's say something that looks pretty unusual, maybe 13, secant for a change. How about that? So again, I select problems pretty much at random. Well, I just look at those if they're of standard type, because I don't want to throw at you something that is kind of odd, but they're all the same. That's the point. So we can just enjoy these exercises. So looking at the exercise 13 with a secant, and that's a 1 over cosine. So if you're given secant theta, right away you can write it as 1 over cosine theta. That's something to know. Or again, at the end of the textbook, you have all these formulas. So it's equal to 3. So I want to pull out cosine, because we always deal with sines and cosines. So it's a 1 over 3. That's our start. Now they want me to know, they want to know what is sine of half angle is. Well, for sine of half angle, cosine is good enough. So the formula above will be utilized, but I need to decide on the quadrant, because that way we decide if that's a positive or negative, right? So that's the key idea. So what they say, it's sine theta is positive. So how can I use that? Well, let me make a picture of unit circle and we'll see everything right in front of us. So unit circle is always with us. Just next chapter, it's gonna be gone and replaced with right train, its little friend. So if cosine is 1/3, that's someplace here. We have 2 possibilities for the angle, right? One above, the other below. One could be positive, the other could be negative. But they also tell us that value of sine for this particular case, you see here, is positive, greater than 0. So if sine is greater than 0, then it'd be here, because there we get something negative. So they always give us the unique result, and now I can find out what this square root is. In fact, if sine is here, so that's my angle. And if I look at the half of it, well, then the value of sine of half angle will also be positive. So I get a square root with a sine plus. But that's the idea. If it's positive or negative, and in this case, it's positive. And this is great. So I'm going to need to put 1 minus. And instead of cosine, this is going to be 1/3. So these problems are pretty nice, I think. You just don't get the best arithmetic, but other than that, it's really nice. And they're all being done same way. If you see denominator, you multiply by that denominator, the top and the bottom, by 3/3, so nothing changes, like multiplying by 1, and I put 3 here. So my denominator cancels. That's why I do this. And I think that's the fastest way and the way that you can make least mistakes. So I highly recommend you to deal like that with complex fractions. I know that some people may prefer their own way. Doesn't matter to me. As long as you do it right, I get very happy. So it's a square root from 2/6, and that's a 1/3, right? Some people can say, oh, I need to rationalize the denominator, right? It's square root 3/3. Maybe that's what's at the back of the book for the answer. But I guess it doesn't really matter. We can just leave it with square root 1/3. So I'm not picking on your arithmetic because we're in trigonometry, right? That's what we really care about. So we went over the chapter 7, and I want to say a couple of words about chapter 8. Just a couple of words, just recall the right triangle so we can get a good start into it, because the next time I want to discuss that section 8.1 and lots of details, and in fact 8.2 and 8.3 will be our key sections for the remaining time. So let us go to next chapter, because we skip last section of this so-called chapter 7, product and sum identities. I think I already told you that last time, because there are some not very nice looking formulas that I don't think they appear anywhere other than in trig classes. So not much use. In calculus, maybe in the whole book you'll find 2 or 3 exercises, and I doubt you might even be asked to do them. But it's good to know that there are some trig formulas and where to find it. So now I hope this textbook will always be with you, saved, when you take this calc classes. And I think these last pages are very, very useful when you have something to do with trigonometry, because it's a nice summary of all these formulas. It's easy to find whatever you need. So what they do here is they give you a couple of very interesting definitions, and that's what I wanted to discuss today. So if you have triangle that is produced by some point on the unit circle, right triangle, right? Then we know that its coordinates are going to be cosine of this angle theta. So this is my theta, theta. And the other side of it will be a sine of theta. Why is it sine of theta? Well, because if you look at the projection to the y-axis or y-coordinate of that point, this is called sine of theta, and that's rectangle because 90 degrees angle, so it'd be the same. So that's for the case when triangle has hypotenuse 1. So what if it's a different hypotenuse? Like say here, they call it as letter C, and 2 other sides are A and B. Well, it's a right triangle, and if it's the same exact angle theta, so the angles of triangle are the same, and according to geometrical similarity of triangles definition, we have same relationship in corresponding sides. What does that mean? Well, hypotenuse is related to hypotenuse here, so C divided by 1. The same way as if I take corresponding sides, so I go big divided by small, B over sine, or if I take C over 1, it's going to be A over cosine. So I divide big by small. As long as you go consistently big by small, that's all you need. Now, you can pull out function sine, which is going to be according to proportion rule, or you could just say this is C, so sine goes to the left and B over C goes on the right. And analogously from here, you can pull out cosine, so you just flip this and get a cosine theta is equal to A over C. But what's most important is to get definition in terms of the sides, such as for angle theta. You see angle theta? This will be the opposite, because you can call with any letters, and this will be called adjacent side. And the third side is hypotenuse. So you can actually write it in terms of these sides, opposite, adjacent, hypotenuse, everything, rather than BC, AC, because you can call those sides with any letters. Nobody wants to remember those A over C or whatever. You want to actually get yourself the little ideas of, instead of B, I have opposite side to the angle. So sine is opposite over hypotenuse. And instead of cosine theta, I have adjacent side over hypotenuse. Now, of course, I can get the other trig functions such as tangent, cotangent, and so forth. And you can definitely do that. Like, for example, if you want to know what tangent of theta is, you just recall that this is sine over cosine. And this way, you notice it's opposite over hypotenuse divided by adjacent over hypotenuse. So hypotenuse will be canceling and you end up with opposite over adjacent. And for the other functions, you already noticed I was working with secant today. Right away I wrote it 1 over cosine. So you're gonna just flip these 3 and get the other 3. That's why we never really care of those. Whenever they say find cotangent, right away write 1 over tangent and find tangent and flip it. So this way you have less to remember and not much to do. So this works for the right triangle with any sides. So I'd like to do one exercise and then I'll let you go, because you deserve to have a weekend. After all that, right? You should be able to have a good weekend and enjoyable days when you, I hope, gonna do a little bit of a homework. Right? And the homework, as usual, do same problems that we did in class, not all of them, you can do some of them. And I just want to introduce you with this section, and next time I'll do a little bit more from it. So here's the set of exercises, and they give you various trainings. So for example, if I try problem number 11, in this exercise, they gave me triangle that has 90 degrees angle and 2 sides. One of them is 2, and the other is 3, and they also call this angle as theta. So please note that angle theta could be any of these angles. Usually we don't care for 90 degrees though, but here's the angle theta. Okay, so what do I need here? In exercise 11, they say find exact value of the 6 trig functions of angle theta. Okay, so I need to know sine theta, which is opposite over hypotenuse. So I'm gonna recall that hypotenuse is here, and this is the opposite, right? And the third side we called as a adjacent. All right, so adjacent is going to be 3, but the question is, what about hypotenuse? Well, we know Pythagorean theorem, right? So if I recall that in any triangle with 90 degrees angle, sum of its sides is equal to sum of squares of its sides equal to square of hypotenuse, then C I can pull out as a square root from a squared plus b squared. And it's always positive because that's the length of the side. Because technically it could have been negative if you do it algebraically, but in our case, it's only positive. So my sides are 2 and 3. So there'll be some kind of number, 2 squared and 3 squared, which is 9 plus 4, right, which is 13. Okay, so hypotenuse is square root 13. Whatever it is, it's fine with me. So now I can do opposite over hypotenuse, right? What's the opposite? 2, hypotenuse is the root of 13. Great. Cosine. Well, that'd be another quotient of adjacent over hypotenuse. Look at this. You have formula, you're done. Here's your adjacent side, 3 divided by hypotenuse, radical 13. Great. Let's get a tangent. Tangent is quotient of opposite over adjacent. These formulas actually I memorized because you encounter them every once in a while. So opposite over adjacent, so that will be the opposite side 2, adjacent is 3, 2/3. You want to find the other 3 functions, just flip them. I guess I'm not going to do that. It's just a bunch of writing. I'd rather bring you again to the last page. That's my favorite page, to illustrate these important new formulas. And that'd be it, because I know I just put a little bit too much on you today. Well, we were refreshing memories on this half angle identities and double angle identities, right? So that's, I think, good when you see it once, then you see it twice, then maybe you do homework, you see it once again. And this way, well, you start to feel better and better about those. So where are my formulas? This opposites and the other ones. They don't have them here. See, sometimes they don't put good formulas there. So I would say that you should probably somehow put them on a piece of paper or something, because this is really supposed to be here. Actually, I don't see at all. Okay. That's frustrating. Well, I see the formulas for the last part for our class, and that's a nice one. That's something we're gonna see next week. But I don't see this opposite over adjacent and so forth. That's disappointing. So I would say that these formulas we should have available for just in case. Because every once in a while in the future math classes, whenever you deal with right triangle, you always can find sine and cosine, and this is very helpful. So anyways, I'm not going to give you a quiz. I think it's something you want to get used to with these triangles and with these sides, and we'll have one maybe next week. So I'm going to stop for today. I'm going to let you go now and have a great rest.